My name is Heather Versillo. I am a CLS that has been with Testoil for almost 10 years, and I'll be hosting our webinar today. But I'd like to present Evan Zabowski, who is our presenter. And Evan is a certified lubrication specialist and has extensive experience training tradesmen and professionals in a variety of fields, including lubrication fundamentals, contamination control, condition monitoring, RCM, FMEA, and used oil analysis. He's also been a member of STLE for over 20 years and has served as the chair of the Alberta section for 8 years. And he's also been an instructor of the condition monitoring courses through STLE at the annual meetings. Currently, Evan's the editor of TLT magazine and has served as the editor for the STLE Alberta section's Basic Handbook of Lubrication, the 3rd edition. And he's also contributed to a number of other publications, such as the STLE CRC's Handbook of Lubrication and Technology. And with that, Evan, go ahead and take it away. And as we are excited to watch, use report interpretation to diagnose overheated equipment. One quick thing, I guess, is if you have any questions or comments, please feel free to put them in the chat or the questions, and we'll make sure we answer as many as possible towards the end of the webinar.
All right, thank you, Heather. So yes, today we're going to use report interpretation a bit differently than probably most people look at reports. And I wanted to start off the presentation with a little bit of humor. It's not super funny, but it just makes us reflect a little bit on why things are the way they are. So you've probably seen a variation of this at some point, but there's always a commentary between, what we know that we know, like how to drive a car or things like that, and what we know we don't know, like maybe speaking a foreign language or something along those lines. But there's also a portion in there of what we know but we've forgotten, which, first.
Oh, Evan, I think you might.
There we go. Somebody muted me. Anyways, I wanted to start off our presentation with a little bit of humor here. So you've probably seen a variation of this particular pie graph, but it begins with things that we know. So that could be things like how to drive a car. And there's always a big portion of what we know we don't know, which are things like speaking a foreign language. And there's a pretty significant portion of what we know but we have forgotten, which for some of us could be things like integral calculus or something along those lines. But what I wanted to focus on was that little yellow slice of what we know but we don't actually apply correctly. It's not that you're necessarily going to learn anything, of great revelation today, that it's something you absolutely didn't know beforehand, but I'm hopefully going to show you how to apply it a bit differently than maybe you've conventionally done. So there could be maybe things that you don't know along the way, but I'm really trying to focus on taking what we probably already know and using it in a way that helps us diagnose some pretty common problems. So what I thought we'd start with is just a little bit about why we use lubricants and then go through a couple of key definitions so we're all on the same page here. Then we'll talk about oil films and the Strybeck curve. This is going to become important to us towards the end of the webinar. And I will present then the case study. This overheated gearbox is what we're going to talk about. What we'll then discuss is how we could diagnose at least some of what's going on with the gearbox without any tools. How do we do it without even using oil analysis or vibration or anything like that? And just to try and wrap up, I think everything people need to know to help read this report, we'll review some common degradation mechanism, just so we're all on the same page there as well. What I'll then do is describe the tips I have for how to read a report. And it's a bit unconventional. It's not, like I said, the usual way people typically read reports. And then we'll go through the actual report. So once we do that, you'll see basically a couple things. One is the unusual way to read reports that's very efficient and helps you get all the information out of it. But two, you will be able to see this common problem of overheating and how even oil analysis can help guide you as to where you should probably focus your efforts. Once we've done all that, we'll come to some sort of final decision about how we go about repairing or remedying the situation. But as you can see the last bullet there, I put a question mark on the verdict of did we get it right? Because the one last thing I'm going to leave you with today is just to help you reassess, I guess, what you think you know that you may have forgotten before coming to these final decisions. Sometimes we're a little too quick to make the decision and we don't realize maybe what we've done. So with that, let's start off with a little bit about why we use lubricants. If you ask somebody, why do you use a lubricant? The number one answer you're probably going to get is something along the lines of it reduces friction and wear. And that's a great summary statement of why we use lubricants, but quick definition. What is friction? Shortest possible definition I can give you for friction is it's a resisting force. So some form of resistance, and it counts as a type of friction. The point, though, is that friction is not always a bad thing, right? Anybody who happened to drive today, which I know many of us are, staying at home, but if you drove, there would be at least two times you needed friction. One would be the traction to get going in the first place, and the other, of course, would be braking to come to a stop. That's why I chose the particular graphic here. If you're familiar with snow sports like skiing or snowboarding, you might know that they wax the bottom of these skis or snowboards to decrease the friction and make the skier or the snowboarder go faster. However, in this picture, that's not waxing the bottom of a ski, it is sharpening the edges. And that's because just like we need traction to get a vehicle going, just like we need braking to make it come to a stop, with the edges of a ski, we are providing a form of friction that gives us control. And that's something I always like to emphasize is that we either design in or leave in by design some friction to any lubricated asset. And it's because that provides us with control. We don't want things to be absolutely frictionless and move in a way that we maybe can't predict or beyond what we would ask of it. And if you imagine taking a pair of skis and making them out of something with a really low coefficient of friction, like say Teflon, polishing them as smooth as you could get them, rounding the edges really nice, and just for effect, spraying them with cooking oil as a lubricant, and then send the skier down the hill, well, yes, they would probably go quite quickly, but they would not have the ability to steer or brake as well as if they had nice sharp edges that provided them with that control. So I just try and make sure we understand just because we have friction doesn't mean it's bad. It means that there's some control. Now, when you define friction, often in a textbook, it says there's two types of friction, static and kinetic. Static friction is the friction you must overcome for an object at rest, whereas kinetic friction is the friction we're overcoming while the object is in motion. In kinetic friction, though, there are three subcategories. Sliding is for anything with a sliding contact. And the best example of that is usually something like a Babbitt bearing because the shaft turning in the bearing is under constant sliding motion. I mean, you can also think of things that reciprocate or oscillate, like perhaps pistons or valves, but a journal bearing is a pretty good example of sliding friction. Rolling friction is something that would occur just like tires on pavement, but would most often be seen from a lubricated aspect in, of course, rolling element bearings. Most people can picture or think of sliding and rolling friction. It's the third one I want to emphasize to you. It's fluid friction. And as soon as you hear the word fluid, don't think of the word liquid. Just because we say fluid, we don't necessarily mean liquid. But what this is a resistance to the medium surrounding the moving parts. And if you think about this logically for a second and ask yourself, why don't you fill a gearbox all the way to the top with oil? Well, obviously, if you've ever seen an overfilled gearbox, you would know that that usually creates a lot of frothing and there's generally some issues with the gearbox. But the number one thing is that you have increased the friction. The gearbox will find it harder to spin the gears through oil than it will to spin them through air, because that oil is a form of fluid friction. And that creates heat, and heat creates problems. So we don't want that. Now, that's not going to be the answer to the case study that I'm showing you, but I'm planting a couple of seeds along the way, making sure we understand why we focus so much on friction. Now, to change gears just a little bit here, we need to go into oil films briefly. So when we describe an oil film, An oil film is designated as lambda. That's the Greek letter that represents the specific film thickness. So we'll just call it lambda for short. And what that is the ratio between the mean film thickness and the surface roughness. Now, for those of you who are a little bit curious, surface roughness is measured by not the mean or the average between peaks and valleys of a rough surface, but by something called the root mean square. So it's the sum of the squares. It's basically an area calculation. It's fun and complicated for those of us who like math. The mean film thickness is the distance from the surface roughness of one surface to the surface roughness of the other surface. So think of it as simply as this. If lambda calculates to be 1, it means the fluid film thickness is the same thickness as the roughness of the parts. So what that would look like would be that the peaks of either surface could potentially come into contact with each other. If lambda happens to be greater than 1, it would mean there's more fluid film separation than there is roughness, which means the parts probably don't touch. And if lambda happened to be less than 1, it would mean that yes, the parts were in constant contact. So I'm going to use this term lambda and go through just 3 of the main fluid films, just so again, we're all on the same page. We all have enough information to know what we're looking at when we read the report. So primarily, we focus on high lambda values. When we design equipment, we would like the lambda value to be somewhere around 4 or maybe a little bit higher. That means there is 4 times more fluid film than there is any roughness of parts, which means from the worst asperity to the other surface's worst asperity, there is still no contact. And no contact means low friction. So this is a very desirable lubrication film, one that we try and achieve by design for low temperature speeds of all moving parts. It's what we want, it's what we like. We'd be happy if we had these kind of lambda values. On the other hand, if lambda happens to be less than 4, all the way down to, but not below 1, we call this particular film mixed lubrication. And mixed lubrication is not a good place to be. That means there's potentially some contact. And the last place we want to see is what we call boundary lubrication, which are fluid films that are less than 1. So less than 1 lambda means, yes, you probably have metal-to-metal contact at all times. So this is seen during start and stop, but you do not want this under operation. So to quickly summarize those 3 in a visual graphic, for those of you who haven't seen this before, there's something called the Strybeck curve. And this was invented by a man by the last name of Strybeck, and he chose to visualize what friction would look like as compared to these lambda values. So friction's on the left, lambdas are across the bottom. And he said there's relatively high friction when lambda is near 0. And it really doesn't decrease until lambda approaches 1. Once lambda hits 1, we actually start to separate the parts and the friction drops. The friction reaches a low point somewhere around lambda of 4. This is why 4 is so desirable. Now, anything beyond 4 is what's referred to as hydrodynamic. Now, there's a narrow band in there that could be elasto-hydrodynamic, but it's all under the hydrodynamic name. And hydrodynamic just references full film, full separation between moving parts. And this is desirable. However, some is good, more is not always better. As you can see, if you continue to the right of the Strybeck curve, increasing lambda can increase friction. So you don't want to be as high as possible. You really want to be somewhere near 4, and preferably a little on the higher side of 4 than on the lower side. So when we design things, again, this is all taken into account, and you can see the calculation at the bottom there that the main factors are things like speed and load, right? That's set based on the operating environment of the machine. Surface roughness is from the finishing that's done to all the machine parts. But the last part is the one we focus on, right? It's the one that most end users have control of, and that is the viscosity of the lubricant put into service. So given that we've covered all these nice definitions, reviewed a little bit of material here, hopefully this isn't the first time you've heard all this before, the last thing I need to make sure we're, again, all knowing before we start looking at stuff is just a quick commentary about viscosity. As we know, viscosity is affected by a few outside influences, pressure being one, but temperature being the big one. most of us know that temperature increases cause viscosity decreases, but two things I need us to know about this. One is that that's not linear, meaning for every 10 degrees, as an example, that I heat up the fluid, it doesn't drop by the same amount of viscosity across a wide temperature range. But the other thing we really need to know is it's not the same rate of change for every oil, meaning I can take two oils of identical viscosity at the same temperature, heat them both up the same amount, and have one thin more than the other. So with all that said, quick review, 15 minutes out of the way here, let's get into our case study. So the case study is simple. It was right in the title of the presentation. We're going to be dealing with an overheated piece of equipment. So in our case, we're dealing with a gearbox here. So this isn't a picture of the actual gearbox in question, but it's just representative. That's our first clue. So this is the easy answer. We know it's running hot. What do we look for next? And a couple things I like to point out about looking for problems is that sometimes we focus so much on what we see that we ignore what we didn't see. And what we didn't see can sometimes be just as revealing as what we did see. And where I'm getting with this, if you want a literary example, is there's a good story from Sherlock Holmes, and it's called The Adventure of Silver Blaze. Now, Silver Blaze is the name of a racehorse. So the problem in the story is the racehorse has gone missing and the trainer has been killed. So Holmes is tasked with finding this racehorse and identifying the killer. So while Holmes goes and collects his data, he makes note of a few things, and then he has a conversation with the Scotland Yard detective Gregory. And the conversation goes like this. He asks of Holmes, "Is there any other point to which you wish to draw my attention?" And Holmes gives a very classic reply. There's even an entire book written on this sentence here because it's so important for us to understand it. Holmes says, "To the curious incident of the dog in the nighttime." Well, Gregory says the dog did nothing in the nighttime. And Holmes replies, "That was the curious incident." Because Holmes's point is that when they were collecting the clues for this, kidnapping, as it were, of a horse and the murder of a trainer, all the witnesses said the dog didn't bark. So what Holmes is realizing is that there's a clue in what didn't happen. And if the dog didn't bark, then whoever stole the horse must have been known by the dog. So basically he's saying it was an inside job. So that's the kind of interesting thing, is that he knows that it was an inside job, and really the only person who could have done it, funnily enough, was the trainer. And spoiler alert, if you haven't read the story, the trainer was killed by the horse. But the point being, what did we not see, right? We didn't find the trainer's footprint beside the horse, a stall, or something that conclusively said it was the trainer. What we realized was something was missing that led us down this path. The more practical example I can give you is this one, if you've ever seen this image before. But this is from the Second World War, and this was a study on damage of returning aircraft. And they were trying to decide where to add armaments, further armor plating to the airplanes. And they looked at this pattern and said, okay, look at all the damaged areas. There's either wingtip, there's the center of the fuselage, and there's the tail section. And so the initial recommendation was we should armor plate all those areas. Those are really important. But this one guy by the last name of Wald, he took a different look at this, and he came to an entirely different conclusion. He said, no, I agree, there's 4 areas we should armor, but here's my 4. He said either engine, the cockpit, and the fuselage between the wings. All the areas that on this diagram, there are no bullet holes. And people looked at him kind of funny because they're like, well, why would you do that? I mean, clearly the bullets get, through the plane here, here, and here. Why wouldn't we do it, to the areas you've identified, which there are no holes? And his logic was simple. He said, every plane that made it back was shot where you see marked. He says, so those are the planes that could still fly. He said, but if they were shot in any of the 4 areas I identified, probably those are all the planes that crashed. And this is what's become known as survivorship bias, meaning that sometimes what we see is biased by the data being changed by whatever the variables are that are affecting your asset or whatever it might be. So in his case, he was exactly right in that by armoring the four areas of the engine's cockpit and the fuselage between the wings, they could actually save airplanes. So just a couple different examples of what did you not see, helping you see what really is the problem. So going back to our gearbox, our case study, we've got an overheated gearbox. So we already know it's hot. We need to go figure out something else. And I said I'd show you how to do this without tools. So what we're going to use are the 5 senses. So if we walk out to a hot gearbox, what might we see? Well, the obvious thing that we're probably looking for is the oil level being too low. That would be a pretty good thing to look for. Now, funnily enough, as I said at the beginning, though, in terms of fluid friction, it could just be that the oil level is too high. But more times than not, we're probably seeing that the oil level is just right. What we would also see as a secondary effect to this overheated temperature is we could see the oil has actually gotten darker. And if we're fortunate and we actually have one of these, we could check for debris on a magnetic plug. These would be things that we could see with our eyes that we could use to diagnose what's going on with the gearbox. On the other hand, we also have our hands. So what might we feel? Well, heat's the given, right? We already know that one. But something could be causing that heat. And one of the easiest answers to that would be maybe it's a misalignment, maybe it's an imbalance. So we might actually feel with our hands some form of vibration. Now, typically coupled with this, we should hear some noise. If it's really out of alignment or really out of balance, it's probably causing metal wear, and we should at least hear some type of noise. So that's now using our ears. If the oil is really hot, then it probably is burning, and therefore it should smell burnt. So that's our 4th sense. The 5th one, I threw this in here as a joke. No, we don't want to go down this path. Please don't be tasting oil. That's an HSE violation, so don't use all 5 senses. But these are the kind of things that we'd be looking for. Now, in our case study, this was done. And what they're expecting in the hot gearbox was to go up and see the sight glass with either a low level or, like the picture here, no oil visible in the sight glass. But as it turns out, that was not correct. That was not the issue. Another thing they were looking for was that potentially it should be creating a lot of noise. And again, that was not what was found. This was not noisy. So we're eliminating things, and in the list of eliminations, we also thought that we might actually feel some vibration, and we did not feel vibration either. So this is why I told you the Sherlock Holmes story and the airplane armoring story, because if you go back to our Strybeck curve and you say to yourself, I don't see that the level's too low, I don't feel vibration, and I don't hear any noise. Those 3 clues are not present. So by knowing what you didn't see, you can actually eliminate being anywhere on the left side of the Strybeck curve, anything to the left of 4, because all of those would account for the symptoms. But because we're lacking those, we know we must be on the right side of the Strybeck curve, somewhere over here, to the right of 4. So if we've got heat, but we're on the right side of the Strybeck curve, what does that tell us? Well, it tells us our lambda value is probably too high. And so now we need to figure out, why do we think that's happening? So as kind of our last little bit of review information before I get into the how to read a report and show you the report, I said I'd talk about oxidative degradation and the mechanisms behind it. So most commonly when oil oxidizes, it's because it's come into contact with oxygen, which is fair because that's the atmosphere. What it accelerates the degradation, though, is generally heat. That's the big one, but it can be accelerated by water contamination. And certainly if there's any metal content in there, it can act as a catalyst towards this. Other forms of contaminants like dirt may play a minor role, and obviously entrained air introduces more oxygen. But the outcome of degraded oil is that, number one, it's probably darker, and it can also have other things that maybe you can't see but help impart some of that color. So they're listed over there. But in quick summary, really what we're looking at is that the most common things to see if the oil has actually degraded would be, visually, it would be darker in color. Through analysis, you should see that the acid number has climbed. The viscosity has probably also increased a little bit. If you're measuring insolubles, those would probably increase, and your nose might detect that the oil has either gone rancid or even developed a foul odor. So when this happens, of course, people are always looking for why did it happen? And the most common cause for degradation is temperature. And if you haven't heard this before, there's a chemist by the name of Arrhenius, and he discovered that every reaction in nature, so this is not unique to lubricants, it's everything, doubles with every 10 degrees Celsius, 18 degrees Fahrenheit rise in temperature. Meaning if you take a bulk oil temperature from something like 70 degrees Celsius, 160 degrees Fahrenheit, and increase it to either 80 degrees Celsius or 180 degrees Fahrenheit, the rate of reaction has now doubled. So it is producing degradation byproducts at twice the rate. So the acid number goes up twice as fast, viscosity changes twice as fast, so on and so forth. That's the number one cause as to why degradation occurs and occurs quickly. Now, another little pointer here, though, is that when we have what I would call moderately high or low-high temperatures, you will see your oxidation values on a report increase by themselves. But if you get to extraordinarily high temperatures, extremely high temperatures, or what I like to call high temperatures, you also get nitration coupled with the oxidation. So that's kind of a little tip I use to help identify the severity of a problem. I expect oxidation, and I know oxidation will be driven the higher the temperatures are for bulk operating temperature. But if I can get nitration to occur simultaneously in a non-combustion application, that's very worrisome to me because it means I've reached some extraordinarily high temperatures. So there's a definite hot spot somewhere in the system when you see nitration. But one of the pitfalls when it comes to interpreting oxidation is not everyone knows what it looks like. And there's kind of a key thing about the visual nature of oxidation. Oxidation typically is very, very dark, dark brown to a black color. But the other thing is it's gritty, it's granular, because it's forming what we say is crystalline and abrasive particles. And this is key to understanding what we're going to see. So now that we've gone through all that, let's take a look at the steps it takes to read a report. So first step is an easy step. When you read a report, read the whole report, top to bottom, be methodical, don't skip around, don't go to the highlighted values only, don't just read the comments, start at the very top, read your whole way down the report. You're gonna learn things as you read the report. Guidance as to maybe what correlates or doesn't correlate with some of the other data. Once you get to the actual numerical data though, here's what we're going to do. We're going to decide if we think the value is abnormal, if it seems amiss in any way, off trend, too high, too low, not what we expect based on new oil, whatever it might be. As we decide it's abnormal, we must classify it as either a cause or an effect. And we don't have to decide what causes have which effects or which effect was driven by which cause, just assign it a cause or effect. Did this occur because of something else? Is it the primary reason something's going wrong? Once we do this, we should be able to group all the causes together in one or maybe two groups. Everything else will just be an effect and we don't have to worry about those. We focus on the causes and we can then decide on the next course of action. And that'll be something that should help us fix the true root cause of the problem. And that's why I say changing the fluid is not really the best idea. Changing the fluid makes the next oil analysis report look great, but doesn't necessarily fix anything mechanical. Right? Very seldom is it the fluid's fault something's gone wrong. I mean, there are times where, yes, maybe it's too contaminated or whatever to continue using, but changing the oil doesn't prevent further contamination. So with that, we will get into the actual report now. So for those of you not familiar with a test oil report, before we get too far into this in terms of reading it methodically, let me just point out a couple of formatting things here. So once we get down to the numerical data, I will be referring to the columns here. So the first column is the new oil column, as you can see identified at the top there. And that is data from a sample of virgin unused oil submitted by the end user to the lab, right? This is not populated by information from refineries or anything like that. It's actual samples of the oil taken right from drums, totes, however people get their oil, and submitted as a comparison. The next column over is the most current result. And as you move further and further to the right, the results get older and older and older. So when you're looking for trends, you read from the right to the left. When you're reading the report, you're focusing on the furthest left result, and you have to the left of that the comparison to the new oil, basically the best case scenario of what that oil might look like. So when we get to the data section, it'll be this column here that I'm focusing on, but I'll refer to the columns to the right and to the left to help us understand if we think the data seems abnormal or not. But anyways, getting to the report and actually reading one methodically. I said read the whole report, start from the top, work your way to the bottom. So here we go. I'll bring up my pointer just so you see where I'm looking and you can tell why I'm saying what I'm saying. But we're going to start here at the very top. So machine type, it says it's a gearbox. It says the sump size is 110 gallons. So this is a pretty big gearbox, takes 2 drums of oil to fill it. Over here, we've got the oil type. Now, unless you're extraordinarily familiar with Alcoa products, you probably haven't learned anything because that 686 is not the viscosity grade. This is not necessarily a 680 oil. But if you knew the product line, you might know what type of oil this was, whether it was an anti-wear, an EP, or an R&O. Most of us are not familiar with Alcoa, so we probably haven't learned much. We have the make, the model of the gearbox. We have over here the date the sample was received, the date the report went out, and of course we have our own customer information just confirming this is in fact our gearbox, right? But once you get to the next section down here, you see all the problems that the lab identified. So they've identified that it had high oxidation, viscosity, and acid number, as well as a particle count. Now, as we get reading this report, you may wonder, why are these not flagged or alarmed in any way? It's because I've removed all the colors from this report. I didn't want you to look at the highlighted values only. I'm just trying to make us focus on the whole thing. Now, each one of these problems will directly relate over here to a comment. So as you read these comments, you will find there's a comment for oxidation first, and then you'll get into viscosity, followed by acid number, followed by particle count. Nothing revelatory is going to come out of reading all this, but it helps give you, what the lab's assessment was of this report. So when you read a report as an end user, you can come to your own conclusion. It may agree, it may disagree, it may complement or supplement what the lab has already said. But generally speaking, in my experience, end users are aware of more factors relating to operating conditions and logistics and stuff like that. They usually come to slightly different answers because they know if they've changed a condition, changed a parameter recently that could account for some of the data shifts. But we'll just go along as if we're the lab here. We don't know much, but we do know it's a gearbox with 2 drums of oil in it. When we get to this area here, this whole top section, we look at the sample date, and if we see the previous sample dates, you can see that they pretty much sample once a month. From there, we see that the hours on the lube oil and the hours on the machine go up by about 700 or so hours, which makes sense because that's what you expect. There's roughly 700 and change hours a month. But a million? That seems a bit questionable. It could be that this gearbox really is 125 years old. That's certainly possible. Certainly seen my share of really old equipment at power plants, but the fact the oil's got the same hours on this, that seems doubtful. So I don't know that this customer is necessarily reporting the hours correctly, but the point being, if you look at all these hours, the hours on the machine, the hours on the oil are identical. So what we can glean from this, the oil's never been changed. Now, why we need to know something like that is so that when we get to this current sample that we're going to read, if we know the oil has never been changed, then we expect that every piece of data will be trending in one direction only. There will be no shifts, no corrections back to new oil from oil changes. So with that, this is why we read everything on the report. We just make sure that we have a prediction for some of the things we expect we're going to find on the report. So let's get into the data and see if we can find any abnormal values. So if we look down at iron, some people think, wow, that seems high. But if you look at the trend, it's actually slowly increasing over time. So that's not really abnormal. Same thing with copper, is a fairly flat trend. Aluminum is a flat trend. And in fact, zinc is a flat trend. I know zinc's a little bit different than the new oil value here, but these are some pretty small numbers. And the fact that it's been flat for this long, I don't really think it's evidence that perhaps a different oil or some other issue has occurred with this particular oil. So in the first half of the report, not really seeing anything that stands out as abnormal. However, go to the second part of the report and start looking for abnormal values. We see that silicon has a flat trend, sodium has a flat trend. Then you get to oxidation. With a new oil value of 1 and a constantly increasing value that is now currently sitting at 85, that does not seem normal. But all we have to do at this point is decide, is it a cause or an effect? Oxidation is usually a byproduct of a degradation mechanism, so it is an effect. So we'll just call it an effect. Now, the next thing on the report that seems a bit abnormal is nitration, right? Flat trend, but new oil value is 3. Probably don't really like that, but flat trend's hard to really get anything out of it. Particle count, on the other hand, look at this particle count. It has increased about 10-fold since the last sample. It's an extraordinarily high particle count. But is that contamination getting in there, or is it something else? Who knows, but it's probably not the cause. It's an effect as well. Something has made the particle count go up. After that, the next thing we probably notice below particle count is viscosity. It should be an ISO 460 oil according to the new oil information, but this viscosity has been climbing from 600 and is now above 700. It is entirely one grade out of grade. This isn't right. Now, do we think somebody's been topping up with the wrong product? No, not really, because look at the trend. It's constantly increasing. I'll wager that is directly tied to the degradation of the oil. So again, this is an effect. Acid number is the next line below, and what do we see about acid number? It is climbing and climbing rapidly. This oil has become very acidic with an acid number at almost 14. And again, is this a cause or an effect? Well, acid number is driven by degradation, so it is also an effect. As you finish off the report, though, you'll see that water has never really shown up, and ferrous wear has been a flat trend. So there is nothing else on this report that we can look at and determine if it's abnormal or not. This is all the data. So the final tally is this. We have oxidation, particle count, viscosity, and acid number, all deemed abnormal, all classified as effects. We actually, in this particular case, did not find a single cause on the report. But if you think about those 4 effects, which we don't need to worry about, we're not going to concentrate on the effects, but what do they all have in common? What would they all have as a driving force? Heat. So heat is causing all those effects. And just as a quick reminder here, we have the Strybeck curve, right? And the Strybeck curve says that you will get high friction if your lambda value is significantly lower than 4. But we determined that was not likely to be the case because we didn't have the evidence that would suggest to us we should expect low lambda values. We didn't have a low oil level. We didn't have the vibration. We didn't have the noise. Where are we on the Strybeck curve, though? Well, the only other place that has high friction is way over to the right. So how do we fix this? If we think that we've got too much of a fluid film driving our heat, how do we reduce it? Right? We want to make sure that we move back to the left here and closer towards that lambda value of 4. Well, the only things that we have to look at is we could try changing the speed, we could try changing the load, we could maybe look at changing the surface roughness, but of course surface roughness would be near impossible to change in an operating piece of equipment. We'd have to replace parts or send it up for machining. Speed and load are governed by the process that it's connected to, so to alter those usually has cascading effects that take great consideration to modify those. The simplest thing that we can focus on that we have the ability to change is the viscosity. And this is a very common driver, and this is a reasonably common enough problem that I see, is that somebody will walk me out through a plant when I'm touring things around, point to something like a gearbox or a pump and say, this is running hot and we don't know why. And I don't even need to see the report, and I can make a pretty solid guess as to what's going on here. And it's exactly what this has all been leading up to. we need to change the viscosity of the fluid that is in this particular application. And if you look around and say, well, why is it using the oil that it's using? It's because somebody, chose it at some point. And if you look at the OEM manual and find that it recommends something different, you often ask the question, well, why did you switch to this particular grade? And the answer inevitably, when people give me overheated equipment, tends to be that either a parameter was changed, like speed or load. They said we started running it faster or harder, or quite commonly they say it was running hot. So therefore we decided to change the lubricant. So to help wrap up this whole example and give us something to think about as we come to the end of the webinar here, is if we had to change the viscosity, how would we change it? Well, we need to make it lower. We need to decrease the viscosity if we want to move left on the Strybeck curve to approach a lambda value closer than to a value of 4. So here's my hypothetical for all you listening in on the webinar. If these were the only two oils you had to choose from, which one would you choose? Right? You visit the lube room, they have a 220 gear oil and they have a 320 gear oil. You're not sure which one they're currently using in the gearbox, perhaps, because maybe you've done all this without any tools, without any oil analysis report, vibration, etc. But they're telling you it's running hot, and you've looked at the oil level, you looked at the noise and vibration, and come to the conclusion, none of that seems to be the driver. I'm wagering we just have the wrong viscosity. Well, of course, intuitively, most of us would look at these two choices and stick with the one on the left. We would pick the 220. And this is why I brought up the point that I did, and this is the point I'll leave us on as we conclude here. But if you actually plot the viscosities of those two products, the 220 is the orange line, the 320 is the blue line, and plot the viscosities across a wide temperature range at a bulk operating temperature of 70 degrees Celsius, roughly 160 degrees Fahrenheit, those two oils have nearly an identical viscosity. But we did say this was a gearbox that was running hot. So if it's running hot, where is the temperature? Well, it's further to the right than that point. So I'm looking over here in the graph. So if you pick the 220 instead of the 320, what did you in fact do to the lambda value and therefore did to the friction and therefore did to the heat? You made it worse. And this is the big point about how things are the way they are, that often people choose something that seems like the right decision, right? Pick the thinner, the lower grade oil to remedy an overheated piece of equipment, but in fact have driven the heat even higher because they failed to take into account the viscosity index of the two products may suggest, as this particular example is, not to say this is true of all 220s compared to all 320s, but in these two oil choices, the 220 actually maintains its viscosity much better than the 320 does. So in high temperature applications over here to the right, the 220 is in fact the thicker of the two products. So that seems almost counterintuitive, I know, but it's because we typically think of these lines as always parallel, but they're not always parallel. And that was my point about viscosity, is that they don't always change at the same rate. So making a simple decision to change the viscosity grade without broad consideration of all the operating parameters, we've in fact made this gearbox run hotter. And getting back to my story, that's usually, like I said, what I find is kind of a common answer when people say, well, why did you change the viscosity from what the OEM recommended? They said, well, it was running hot. So we put the thinner oil in. Well, if these were the two choices and they put the 220 in, they made it worse, and that's why we're still where we are. So with that, I will conclude the webinar. Hopefully that's given you something to think about, that, like I said, it's not always what you see, sometimes it's what you don't see that can help tell you what is really going on, but also to make sure we really think about some of our decisions and say, yes, I considered all sides of this particular decision and not just blindly going in, on faith or intuition. So with that, I'll turn it back over to Heather and see if we've had any questions along the way.
Thanks, Evan. That was really great. And it's one of my favorite webinars that we do. But we actually do not have any questions at this time. But if anyone has anything they're interested in asking Evan after the fact, his email address is right there. Please always feel free to reach out to him or myself, and we'd be happy to get you any information that you're looking for. Otherwise, Evan, thank you very much for your time today, and everyone have a great day.
Great, thank you.